In this video, we will visit another branch of machine learning called reinforcement learning. In particular, we'll talk about introduction to RL, Markov decision process, and Q-learning. So here we go. There is three different classes of learning problem. We have seen supervised learning when you given a data X and label Y, and the goal is trying to learn a function to map from X to Y. An example here, given an image of an apple, you want to provide a label saying this is an apple. We also talk about unsupervised learning when only the data provided is X and no label at all. And the goal here is trying to learn an underlying structure. For example, given an image of a something, you're trying to find something that are similar to that thing, right? So there's no label of an apple here in this case. So today we're going to talk about a different type of supervised learning called reinforcement learning, where we given state and action pairs, and the goal is trying to maximize the future reward over many time steps. So an example is, given this image of an apple, you might learn that eat this thing because it will give you energy, keep you alive. Now let's start with a video
Go is the
on
world's oldest
Game of
continuously
Go
played board game.
and
It
reinforcement
is
learning.
one of the simplest and also most abstract.
Beating a professional player at Go is a long-standing challenge of artificial intelligence.
Everything we've ever tried in AI just falls over when you try the game of Go.
The number of possible configurations of the board is more than the number of atoms in the universe.
AlphaGo found a way to learn how to play Go.
So far, AlphaGo has beaten every challenge we've given it, but we won't know its true strength until we play somebody who is at the top of the world, like Lee Sedol.
A match like no other is about to get underway in South Korea.
Lee Sedol is to Go what Roger Federer is to tennis.
Just the very thought of a machine playing a human is inherently intriguing.
The place is a madhouse.
Welcome to the DeepMind Challenge.
The whole world is watching.
Can Lee Sedol find AlphaGo's weakness? Whoa. Is there, in fact, a weakness?
The game kind of turned on its axis.
Look at his face.
That is not a confident face.
It's developing into a very, very dangerous fight.
Ooh, hold the phone. Lee has left the room.
In the end, it is about pride.
I think there's something went wrong.
Yeah, it's made a mistake.
He's got to pronounce a miracle.
These ideas that are driving AlphaGo are going to drive our future.
This is it, folks.
It's a documentary on Netflix, so if you want to watch the whole thing, you definitely can. But today we're really talking about what kind of technology behind the DeepMind, who's a machine behind playing AlphaGo with Lee Sedol. So let's look at machine learning at a stack, right? So what can be learned here that we see? So number one is the sensor. Like we feel the first step machine learning collecting data. So you need sensor like LiDAR, camera to collect images, radar, GPS to collect your location, stereo camera to capture 3D videos, microphone to capture sounds, networking to transmit data from one form to the next, and the IMU or initial movement unit. You can think about it, it's a combination of a accelerator and a gyroscope to capture your body movement. So these sensors are all taking data and put it into a machine learning system. And then the next step is what you're already seeing a lot of time, which is a representation learning to transform from one representation to the next, and richer representation, so on and so forth. So that's what we have talked about so far in the course. But then the next step in the stack is to extract knowledge or reasoning. So you might have an application machine learning about image recognition. So if this look like a duck, and then you have an application to audio recognition. If they quack like a duck, and then you also have an activity recognitions model when it's recognize this thing swim like a duck. So now it's have very good abstractions of what a duck is as an entity. And then the final phase is taking actions, planning a series of actions or course of actions accordingly to the knowledge that it have. And then from those actions, it may be able to collect more data from the sensor associated with the system. So if you look at a deep learning, here's a full stack of deep learning. But if you look at the deep reinforcement learning, then you have the entire stacks here. So the promise of deep reinforcement learning is certainly larger than deep learning itself, and a very exciting field of machine learning. So exactly what is reinforcement learning? Reinforcement learning is a set of problem where we have an agent interacting with an environment which provide the agent with some numeric rewards or observation. So at each step, the agent will do the following. The agent will execute an action and then observe a new state applied to the agent and also receive some reward. And the goal here is trying to take the series of action from a policy in order to maximize some reward. So there are a lot of examples in reinforcement learning. I think the most popular example is the cart pole balancing problem. Imagine you have a freestanding cart pole on a cart and your cart is moving. And so what happened is you're trying to balance this pole on this moving cart. And so the state of this problem is the pole angle, angular speed, cart position, horizontal velocity, and the kind of action you can take is the horizontal force that you can apply on the force to make it go faster or slow it down. And you notice when you go faster, then the pole tend to moving backward, and you move slower than the pole leaning forward, so that you keep balancing it. And while you balance it at the pole is upright, you receive some reward. Another example is the grasping object, where you can see, in the robotic arm trying to grapple some object. So the goal here is trying to pick up an object with a different shape. The state that you have, maybe you have a camera to capture whether the object, you can see that where the object is and move the arm toward the object. The action that you can do with the robotic arm could be move arm, grasp, and lift the object or drop it down. And it is the reward that you can receive is positive when a pickup is successful. Now into the video game world, if you think about video game, a game of Doom, for example, here, the goal for this environment is to eliminate all opponents, and you receive a state at raw game pixel of the game. And the action that you can do is similar to the action in the game. You can shoot, dodge, run, walk, move left, move right, or take no action, right? And then the reward could be positive when you eliminating an opponent, and negative when you or the agent is eliminated. Now, more serious example into the self-driving car competition from the MIT called Deep Traffic, and the goal is trying to train that agent that successfully navigate through traffic. So the state that you receive is a 2D state at a grid where each cell is the speed of the vehicle inside it. And the action that you can do things like accelerate, decelerate, turn left, turn right, or keep course and no action. The rewards will be positive when the high speeds is maintained. So you had to go through traffic while maintaining high speed. Well, not really recommended, is it? But that's the context of the training problem. Okay, RL also observed in humans. I'm showing you here a picture of my son. He started to learn how to walk last year during Halloween, so he was a lion here. And it's so interesting that humans appear to walk through a very few example of try and errors, right? And so far the machine learning we learn gets so much try and errors, or so many examples. So it's amazing that he can walk with very few examples, and a few fall down, then he was doing fine. And his rewards here is that he loved bubble, so we give him a bubble so he can run toward, right? But learning how we learn to walk through an open questions. And we can see there are a few possible answers here. Number one could be our hardwares are very capable of bipedal movement. We have a 220 million year of data built right into our DNA. Maybe imitation learning, right? He observed other human walking, and so he started to walk to imitate. And that which make a really interesting experiment, whether if the child never observed any human being walking, would he or she still be able to walk? Right? And then finally, he might have some sort of algorithm happen in his neural network, probably something better than backprop or HUD. Right? So what are the real-world application of reinforcement learning? We see that they have Mars rover and the robotic explorer. We have application of playing different Atari games. We have Go Player that you see in the movie. If you have a Nest thermostat, you notice that this also adaptive adjusts the temperature based on the data it receives. And finally, it can use a lot with the stock trading these days, where the majority of the stocks are traded by automated machine. So we first start with a Markov decision process, which is a mathematical framework formulation for RL problem. And the interesting about this Markov decision process is that it have a property of the current state will completely characterize the state of the world. Just to simplify the problem, make it easy to solve. So here's an example of the Markov decision process, and you can see all the states are in the circle with an S, and you can go from one state to another state depending on the action that you take, and you might receive some reward, like a little heart here, or you receive some punishment or negative rewards at this fires here, and you can take different action. Maybe this action will move it in one state to the next, where other action would kind of get you in the same place. So mathematically, we have a set of set. So these are different set. So S is a set of possible state that you can be in. A is the set of possible actions. R is the reward distribution given by a state or an action. And P is the transition probability distribution to the next state. So given a state, it would and an action, it gives you the next state. And finally, we also have something called discount factor that we're going to talk about a bit later. So, Markov decision process start with the environment sample the initial state S0, which is from the transition probability of S0, then repeat the following. The agent will select the action AI, A, T at time T, based on the possible set of actions, and then the reward is sampled from the environment, right? And then the next state also sample from environment given the state and the action, you get the new state back. The agent also receive the rewards and the next state, so it update its own state. And the objective here is find strategy that maximize the future reward, right? So you can think about it as a series of state, action, and then rewards. And this would happen through time. So this is at time 0, time 1 you see here, and they keep going, so on and so forth, to time n until you reach the terminal state. The terminal state is maybe when you achieve your goal or when the agent dies. Okay, so maximize future rewards. We had to look at the future rewards slightly different than before, because the future reward, if you think about the future reward, it's just a summation of all the rewards that you collect over time. You might run into a bit of a problem. And the problem here, why you try to maximize this sum, the agent would trying to basically live forever. It means that it's trying to keep collect more and more and more example, which might not be what you want. And it's also not reflect the reality. In fact, the reality typically follow what called the discounted future rewards, where each of the reward of the future will be associated with what called a discounted factors, right? So instead of just a summation, it's now a weighted sum, and the future reward going to be associated with some discount factors here. And the further step in the future, you're going to have a slightly higher degree of this discounted factor, right? So on and so forth. And this kind of factor would range between 0 and 1. Now, the good strategy is that the agent would be choose an action that maximize the discounted future rewards, not the future rewards. Why is that? There are a couple of reasons. Number one is that the environment is associated with some uncertainty. And even worse, sometimes you can't observe the environment completely. You have also partial observation. So the reward never is a certain from the uncertain environment, right? And the other reason is you think about real life, right? if I give you $5 today versus if I give you $5 10 years from now, which one would you take? Right? So you certainly think like the $5 from now would worth more than $5 in the future. That's justify why you need that discount factors, right? And another example is, whether you want to live it up today or you save the money for tomorrow. So even though it's uncertain, you can have that choice, right? So point is, we're trying to maximize the discounted future rewards, right? Not just the future rewards. Okay. So you can take an action given a Q function. So we're going to learn about the Q function here. A Q function is nothing but a expected value of a state given some actions, right? So it's just an expected return or the expected reward given some state and action. Okay, and the policy pi is a function that maps from S to A that specify what action to take for each state. So the agent can have a policy pi of S to infer to the best action to take given some states. So a policy, think about it, it's like what the best action to take given a state. So what a policy is, just what I said before, an action to maximize the expected future rewards, or Q value in this case. So you have an argmax function here with the Q value, and you take the action that maximize this amount. Okay. So typically we use a simple example like moving in the grid world, and in the grid world, you have a number of terminal state, which is the goal state that you want to accomplish using the least amount of action. And the possible action here is moving left, right, and down, right? And you may get some like negative reward if you move to like a state that don't have anything, right? So it costs energy to move. Maybe that's why you get negative reward. Okay, so you might have some policy to move in this grid world, and your policy might have like random policies, so you don't really care in any given state you should move random directions, right? Or you can have an optimal policy, whereas given a certain state, you know what is the best action to take to move yourself to the terminal state or the goal state the quickest, perhaps. So this is the optimal policy. There's 3 types of reinforcement learning. And so a reinforcement learning agent may be directly or indirectly trying to do one of the followings. It may try to do model learning, which is model environment, then use it and update it often. This model learning is typically difficult because the stochastic nature of the environment, and plus the agent cannot completely observe the environment at all times. The second is the value learning or Q learning that we see the Q function. So the Q learning is to learn the state action value and then trying to choose the best action and then explore if necessary. We're actually going to go in that in a little bit. And then the third type is policy learning or policy gradient, which you learn the policy directly that map the state to action and sampling that policy. We actually will learn about gradient. Policy gradient in the next video. Okay, and if you map everything here, it's a sort of a mapping of all of the different type of model learning, value learning, or policy learning, or some hybrid method that we will learn next as well. Okay, so let's talk about value learning first, or Q learning. And the Q learning here is just solving the optimal policy. So by learning this Q learning, you actually attempt to solve the optimal policy as well. So start up using a state action value function Q given 2 parameter S and A as the expected return. And you learn a policy that maximize the discounted future rewards, right? So this is actually an approximation of the Bellman equation. And this is the Q table or Q function actually independent of the policy. All you have to do is keep updating all of the state and action pair in the Q table. So how do you update it? Here's a formulation, right? It looks complicated. It's not that bad actually. So you have some updated Q value, and this updated Q value is going to base on some old Q value. And then you have a learning rate, which determine how fast you should update these things. You have a reward where you're taking into account what happened if I take this action, I'll get, what reward at this current step. And you also have some discounted factor to account for the uncertainty of the future. And you also have the future value, Q value, upon selecting the best actions. So this Q value here is get you into another state where you take the best action, right? And this one is just the O value, Q value, okay? So that would be the formulation you use to update the Q table in Q learning. And there is another way you can look at this compared to other machine learning method that we learned before, is that you can take this OQ value out of this parenthesis. Right? So if you take this out, you do some arithmetic, you pair this one, it will become 1 minus Q here, right? Yeah. And then you also have the other things inside this learning rate. So inside the learning rate now you have the current rewards and the discounted future reward upon taking the best actions, right? So this would, maybe for some of you, this would make more sense when you say, I'm going to update my Q value based on some ratio of the O value and my updated one, given the best future rewards. So in code, you can think about it like you want to update a two-dimensional array or a table here with all the row represent different possible state that you have, and all the column represent all the action that you can take. So the action here may be up, down, left, right. You have 4, and then the number of 4 states here. It could be a lot more states that represent different state that the agent can possibly in, maybe like 4 block into that grid world, right? So the code's actually pretty straightforward. You initialize it maybe randomly or depend on how the environment would give you something initially. You avert initial state and then you repeat the following. You select an action to carry out and then observe the reward and the new state and then update the Q table using this formulations here and then update the state. And you keep repeating that, update that Q table until terminated, right? So as you update the Q table, you may end up with these all the values, and these values basically indicate what best action to take. So you can see here, if you say you start at this state, the best actions here are the highest Q value. So it maximize the Q value at this state, and you take action 2. Maybe when you take action 2, it moves you to state 1, and in state 1, now you look at the Q table to figure out what action to take, which is this an A2, and maybe action A2 gonna take you to state 4, and then you look at state 4, what is the best action to take from there. So that's how your agent can move from one state to the next, given this Q table. So having this Q table in your hand, you now know how best to move around in a grid world, right? So yeah, you always find the Q table at the previous step, and then you try to take the argmax with the best action. We should talk about that with the loop in the code. And so this will be optimal policy when you move in the grid world. Know that this is the physical grid, and each of the cell in this going to be a state in the Q table, each of the row in the Q table. And then you still have 4 column, which indicate 4 actions here, right? Awesome. Now, what I really want to touch on also the idea of exploration versus exploitation. So the Q table is saying that you only take the best actions, but sometimes it might not be the best idea, especially initially, right? So initially, maybe you don't have a lot of idea about the environment at the beginning, like maybe your Q tables are not really update quite good yet. So what you want to do, you want to have to try to having a exploration, sort of a randomness to your actions, right? You don't want to take the action that return the best Q value right away, especially initially. You rather want to take sometime a random action, right? And that random action is what called this epsilon greedy policy. And the epsilon greedy policy, it always take an action with probability 1 minus epsilon of performing the best or greedy action, otherwise a random action. And epsilon here is a small number, so then maybe like if it's 0.5, then 95% of the time you would take the best action, go greedy, right, at the time, otherwise you take a random action. So at your Q table more mature or more stable, you may give toward the greedy policy of taking the best action at each time. So the epsilon would go to 0. All right, some example for you. In restaurant selection, exploitation would be always go to your favorite restaurant, but then your life would be boring, right? You always go to the same restaurant, the best restaurant for you. Maybe some exploration would be you check out a new restaurant sometimes, right? The one that you find online, perhaps. Banner ads, exploit would be show the most successful ad. Explore would be show a different ad. Maybe you're taking your chance. Oil drilling, exploit would be only drill on the best node location that you know have oil. Exploration would be trying to drill at a new location. Game playing, exploit would be when only trying your best move, the move that give you best chance to win. Or exploration would be trying to do some experimental move. So that's it for now. Recap. Reinforcement learning is one of the most exciting fields in machine learning. In Markov decision process, a good strategy would be for the agent to always choose an action that maximizes the discounted future reward. And Q-learning is to learn the state action pairs and act on choosing the best action and then explore if necessary. So these are the very fundamental concepts of reinforcement learning. Next, we're going to dig deeper into the deep reinforcement learning dealing with neural networks. So in particular, we will talking about in the next video, deep Q network, policy gradients, and actor critic algorithms. We'll see you then.